Okay, so it's time, and I guess we can start. So, hello and welcome, everyone. Good morning. I guess for most of the people, it's still morning, but for me, for example, it's already afternoon. So, good morning to you as well. So, it is the third and the last day of the conference. So, I hope everyone is having a great time. And in this session, we are going to talk about some practical applications of machine learning in software testing stages. And firstly, let me introduce myself. My name is Mesut Durukal, and I'm working as a QA engineer. I have an experience of more than 12 years in QA area, and for now, I'm working for Siemens, located in Istanbul. And lately, I'm dealing with some adaptations of machine learning in different software testing stages. I mean, we are practicing some different applications on different parts of software testing lifecycle. And you can find some contact information for me over different platforms. And please do not hesitate to reach out to me during the presentation or even afterwards. And let's have a look on the brief agenda for the talk. As I told, we will see some adaptations of machine learning in software testing stages. And firstly, in the first part, I will remind you briefly the working principles and the background of machine learning algorithms. And then we will see what kind of applications we can do with the help of machine learning. I mean, what is the relationship between machine learning and testing activities, right? And finally, I will share you a case study in which we will see a real-life scenario, how we pulled machine learning into the play. We will see some results and some representation of the study in that real-life project. So let's start with the first part, the introduction section, in which we will remember the basics of machine learning and how we can adapt machine learning into software testing lifecycle. Firstly, let's quickly remind the background of it. Of course, firstly, why are we talking about this, right? I mean, why are we searching for adaptations of machine learning into software testing? Why is the necessity, and why are we doing this? Why are we bothering ourselves? Because we have some challenges, right? In software testing area, we have some challenges, and today's world, nowadays, these challenges are much and more challenging compared to the previous activities, because there's a great rivalry in the software market today. Everyone is trying to be the first in the market, so they are all in a rush, and they are adapting the latest technologies, the latest technologies into their product, and they are adapting some different integrations to different platforms. All the platforms are connected. There are lots of integrations between them. So there's a very complicated context which we have to ensure. We have to test and verify, and we have to do that in a very limited time. We have a very short time because, as I told, everyone is in a rush, and sometimes in deployment times we have only a couple of hours for the testing window. It's a very limited time, and we are living in an agile environment, so we encounter lots of changes, lots of updates in the product and in the features that we test. When I'm testing something, then within the sprint, then I learn that the features updated. So I have to adapt quickly and immediately. So in spite of doing all these, or instead of doing all this manually, we adapt automation processes into our life cycles, right? And similarly, we try to adapt machine learning into our processes to get some help from them. So we are searching for some help from someone, and machines are a good and a powerful candidate to help us. And if we check whether they can really help us, yes, we know that they are already designed by human beings, so they have a limited capacity in some manners, and they are machines, they are not human beings, so they don't have emotions, right? But we can argue about it if having an emotion or not having an emotion is an advantage or a disadvantage. Sometimes we as human beings have social aspects in our lives. So sometimes as a tester especially, these manners really is of great importance. But apart from all these, machines have some definite advantages. Let's check all these. First of all, they don't get tired, right? Because as the human do, at the end of a long working day, we can get tired, and it is very likely for us to overlook some weaknesses or some bugs at the end of the day. Because I'm already tired, I want to go to home immediately, and I lost my motivation at the end of the day. But for machines, it is not the case. It is performing at the same level all the time, or at least it is performing almost at the same level all the time, and they don't get forget. Another feature or another advantage they have is they don't forget. I mean, if you put an information inside, unless you delete it, you remove it, it is always there. It doesn't forget as the people do. It is another advantage. And finally, we can immediately add some resources from the machines when we need it, right? For example, sometimes you need some extra resources, and it is not that easy to add an additional headcount. I mean, you cannot adapt immediately a person into your project because you need an adaptation time. But for machines, it is not the case. You can, if you need an extra resource for the machines from the machine side, then you can immediately create some additional resources. You can create some virtual resources, and you can immediately increase your resources, right? So those are all the advantages of machines. And we already started to see that they started to overperform. They started to beat human beings. For example, in some games, we see that in, for example, Go, which is a very tough, which is a difficult game, the machines, the robots started to beat the champs of the game. So in some manners, they started to overperform human beings. So if we can do it properly, we can really get or take advantage of the machines, and we can get really some help from those in our process. And we already start to see that they are already being used widely. I mean, on this table, I summarized some of the applications or some of the platforms, some of the commercial platforms that use machine learning in their sites or in their applications. These are mostly related to software testing purposes. But beyond this, we already see the machine learning based applications in our daily life, right? For example, when I'm texting an email, or when I'm responding to an email which I have in my inbox, I see that after I type something, then it is automatically completed, right? For example, I write dear blah blah, and it is completed by the name of the sender. And when I'm, for example, at the end, when I'm writing best, then it is completed with regards, right? Because it knows that it should be most probably best regards, most probably. So the machine already learned what it can be, what it is most likely to be. So really learned from the past experiences. It observed what most of the people write, in what sense they write their sentences, and they learn how it works. So learning here is very important, and in a very short while we will check what learning means. But when I'm seeing all these auto completions, then I'm happy, right? Because it makes life easier for us. I don't have to bother myself to manually write all the sentences. Those are all completed by the machines, by the robots, by the algorithms, and I see that they are working really very consistently. They're really the sentences, the rest of the sentences, really the one that I want to write. So it is working very properly because it is observing a wide range of data, and it is experiencing, and it is learning really very consistently. So we are talking about learning, especially. I'm emphasizing what learning means. So we should know, discuss on this, what a learning means. So it is something different than memorizing something, or it is something different than being explicitly programmed by someone. So Alan Turing was one of the first guys in the academy, which was asking these questions in 1950s, as I remember. He had some articles, and he was asking these questions to the community: if machines can think, or if machines can learn. So what does he mean? Let's consider this issue over some sample scenarios. For example, on the image on the slide, you see a baby trying to touch to a hot object on the oven, right? For example, let's take a cup of coffee. When he touches a cup of coffee, then he feels the pain in his fingers or in his hand, right? And for the next time, when he sees another hot object or another object which is very likely to be hot, for example, a cup of tea, then he will not touch because he has some already experiences. He already learned how it works. If he touches to a hot object, then he will feel the pain in his hand. So, but he did not memorize a cup of coffee because when the next time he sees a cup of tea, it is not cup of coffee. It is something different, but it is the same way it works. So he understands. He learns the mechanism or the working principle of the subject. So he did not memorize, but instead he learns how it works. And when I ask what this image is on the bottom of the slide, we can all answer, right? It's a special kind of chair, or it's a coach, whatever it is. But we know that what it is, right? Because okay, it is not a traditional chair. It doesn't have four legs, but we all know that we can sit on, and chair or couch is something that we can sit on, right? So this is we know that what it is. So we learn how it works, and for the upcoming samples, if I show you another one which is not exactly the same shape with this one, if it is a different one, even if it is a different one, you will know what it is. What it is. So because you learn and you has you have lots of experiences, which is enabling you to know how it works. And we can see that it is really very similar to our biological learning. For example, when we see a cat, when there's a cat in front of us, we see it with our eyes, and on our brains we process to understand what it is, right? So when we see the steps for this learning or for this understanding procedure, there is a gradual processing underlying. I mean, first of all, when we first see the object that is in front of us, we see first the outermost frame of the object. First of all, we know that it is size and dimensions, and we know that it is not a lion, right? Maybe it can be a cat, but it is not a lion because it is not that big. Because we first process the outermost frame, and then we will one by one, then maybe the other features, maybe it has some ears or uh, what are the what their eyes look like, or lots of the different features we can take into hand, and we can process accordingly. So there's a gradual and processing in this process, and most of the machine learning procedures are inspired by our biological learning. For example, deep learning is again a consisting of a neural network which is existing in our body. So we will see lots of algorithms which is looking very similar to our biological learning and the mentality as well. For example, let's quickly remind how it works. Of course, for the machine learning studies, data is very important, right? Because we have to have enough data to teach to machine how our system is like. If we don't have enough data, then machine will not be fully understanding our system. So we should be giving enough data and the key information to the machine to teach it how our system works. For example, I will say to machine that, okay, in this kind of circumstances, my reactions is like this, okay? And in some other actions, I'm taking these reactions, okay? I'm teaching all these to the machine, and machine is analyzing all this data, and he is, or it is constructing a model. It understands that, okay, for this range of data, I should take this according reaction. Or for another range of data, I should take another reaction because it learned from what I taught to it. It learns according or over the data, and when he constructs a model about the system, then for the upcoming samples, it can predict the related or needed action items. It can make some predictions, right? Because it has already the model, and according to the model, the output is defined already according to the input. And we can, of course, update our model in time, because when we evaluate if it works well, then okay, we can let it go. But if we observe that it should be improved, then we can optimize. We can play with our parameters, play with our weights to update our algorithm or our model. And for the testing, since we should talk on the relationship between the machine learning and testing, let's discuss how it works on software testing. Actually, it's again not very different, and it is not again magic. So when you ask me to test your system, if I was or if you were the customer of me and you were asking me to test your system, then my response would be, okay, I can test your system, but first of all, teach me how your system works, right? Or teach me how your system is supposed to work. And what I can do is to get some documentation from you to observe what kind of inputs I have or I can have in your system. And according to those inputs, what outputs I will observe. Or I can do an exploratory testing. I can explore your system. For example, if it is a website, then I can go to your website. I can click on buttons to see what it happens. Or I can navigate between pages. I observe and I learn how the system works. So for the machine, it is nothing else. It is nothing different. So it observes by randomly clicking, randomly taking some actions, randomly providing some inputs, and observing the outputs. For example, if, okay, we discussed how it works on the UI side, but if it is an API, then what the machine can do? Maybe it can send some requests, right? It can perform some queries, and then it can observe the responses. For example, maybe the first response would be an unauthenticated one. Then machine will observe what the system is reacting across unauthenticated queries. Most probably, the response would be a bad response, which is 400, 401, 403 something. So the machine is learning that, okay, when in the future, when for an upcoming sample, if the request is an unauthenticated one, then I should expect a bad response or a bad response code, which is 400 something. So it is the interpretation of the machine from the past experiences, and accordingly, it can take various action items. For example, it can generate some test cases. We will see in the rest of the slide. According to this learned experience, it will generate some test cases. It will execute the remaining test cases. It can do lots of work automatically in terms of automatical processing to get rid of the manual effort and to reduce the time that we need. And accordingly, we can have lots of different problems. And according to our problem, we can apply different algorithms. For example, our problem can be a supervised learning problem, or it can be an unsupervised learning problem. For example, I will show you a case study at the end. It is for example, there are some labels on the data. For example, those are the bugs coming from Jira. I export my Jira list in which I have lots of bugs created by different people in the team. And in the bugs, I have some labels. For example, all the bugs are labeled with some severity classes. Some of them are in severity 2, some of them are severity 3. Then I understand that it's a supervised learning because I have some labels. And I can apply some supervised learning solutions. But otherwise, if I'm dealing with some clusters on the bugs, then maybe it will be an unsupervised learning problem. and I can apply some unsupervised learning solutions accordingly, right? So we can choose according to our problem. And after this quick check of the background of the issues, then let's concentrate on what can we do with the help of machine learning. What can we do together with the robots or with the machines in software testing life cycles. I will try to do that. I will try to investigate this in a systematical manner. I mean, in a classical software testing lifecycle, we have some stages, right? Starting from the analysis of the requirements, then after we analyze the requirements, then we design our test cases, and then we implement and we develop our test code, and then we execute them. And finally, I deal with the maintenance of the test code, the test executions, or maybe I'm creating some bugs if I detect some vulnerabilities or weaknesses on the product. And I continue with the maintenance of the test code. And in all these subsequent processes, there's a relationship between these two. I mean, we are building a traceability between the requirements and the test cases we create, right? There's a traceability, there's a relationship between these two. And with the created test cases, the test code is related to the some test case, right? Because in all of our test classes, for most of the time, we have some test case IDs, which is coming from the design test case. There is an input and output relationship in all these two subsequent processes. So we will make use of this relationship to observe the input and to observe the output. And for the upcoming samples, we will, according to this model, we will create our upcoming predictions. So let's start with the first stage, which is the test definition stage. We all already told that the first step that we have to test something is to define what we will test, right? And as we already discussed, the first thing is to observe what I have, to observe what possible scenarios that I have, what I can do on the system, and for all my actions, what I will be encountered with. What will be the output of my actions? What will be the reactions of my actions? So I will observe all these pairs, and by observing this relationship, input-output relationship, I will construct my model. So and again, it will be it can be an API, it can be an UI, whatever it is, just on the system. All I want to say, or all I have to do is to construct the working principle model of the system. So let's go over some examples, and I hope it will be more clear while saying this on some examples. For example, let's consider this sample scenario. Now we have a library API, okay, and we have some books inside the library, and I can query the books from the library, right? And I see the entities, the books entities coming from the API, coming from the response. And in the books entity, there are some separate book entities. And in each book entity, I see the ISBN number, the price of the book, and the published year of the book, right? I can observe all these. No one taught me before. Now I'm observing what there is in the response. And another thing that I can observe is an ISBN number is consisting of a string value, a large string value. Inside there are some numbers. And the price is most probably a double value. And the year, the published year is some value in the integer type, right? I observed all these. And so the next thing I can do is, okay, then for the next step, I can define a test case on my own, because I already know what is inside the entities and the data types. So let's define a test case automatically. It can be a negative case. For example, let's put we already know that a string value should exist in the ISBN field. So let's put a integer value with a bad format, right? Just maybe the dots, the commas, and some bad formatted value. So in this way, what we will expect is most probably a bad format, bad format response code, right? maybe 400 or something. Or we can generate a test case which is trying to post some data inside, right? For the next time, if the first was a get query, then maybe we can define another case in which we are querying a post request to the server. So in this way, after observing how the requests work and how the responses are looking like, then we can generate or continue to generate the upcoming test cases related to the other features of the product. And the UI side, the front end is, I think, much more interesting. For example, on the slides, we see lots of baskets, right? All different types of baskets, but still all of them are basket images. And if we are dealing with an online shopping site, then we know what a basket means, right? For example, if I'm trying to buy something online on a shopping site, I know how I can do it, right? Because normally no one taught me how to use that site, but I know it. Because how do I know it? Because I already used some other sites to buy something online, and for most of the sites, I know that, okay, if there's a basket, then I know that it is the shopping cart of my order. And if I order something, then I will see some numbers on the basket, most probably. I know that from my past experiences, so I learned it. I learned how it works. So for the new site, I can test how it works. If I put some items in my basket, then when I go inside my basket, I expect to see that item in the basket. So that is my expected result. So as a tester, I already, I already defined or generated a test case. I see what is on the page, what items exist on the page. And if when I see there are some baskets, I understand that it is a online shopping site. And I can generate to whether I'm seeing the ordered item inside the basket or not. So I fully automatically generate this test case according to my past experiences and learnings. And after I generate all my code or all my test case, what I have to do next is to develop this, because I'm automating my test cases and I'm developing my test code and I'm integrating all these into my pipelines. So I should develop test code, but it is sometimes a cumbersome issue because it needs some manual effort, and sometimes it is really time consuming, because after I develop my code, I send to a code review, another colleague in the team is reviewing the code, then maybe sending it back to me to improve my weaknesses, to improve the anti-patterns in the code, and it is really time consuming. But what if the machines do it automatically, in a systematic way, in a proper way, without any anti-patterns? Can it do it? Yes, it can really do it, because let's check this example on the screen. For example, for the input-output pairs, for a human being, it may not be very straightforward to understand the relationship between those two, but for a machine, it can immediately observe what the required operations to reach to the output. For example, from the input, how can we reach to the output? After observing for a while, we can see that all the values are multiplied with 4, right? For example, minus 17 is the first entry in the input, and we can see minus 68 in the output at the last item. And minus 3, and we see minus 12. All the entries are multiplied with 4, but we see that all the positive values are filtered out, because we see only the negative values. So the operations are really very obvious. So we have to, we need a multiplication operation, then we need a filter out operation, and finally all the values are sorted, right? Starting from the biggest to the smallest. So the needed operations are obvious, and after finding this, to adapt the needed code to implement this operations is very easy. So the tough part is to understand what operations are needed to reach to this output. So as I told, the machines are very experiencing some different codes with a huge data set, it can learn which operations can or are needed for these operations, and it is detecting the probabilities of the needed operations afterwards, and it just adapts the needed code for these operations afterwards. It is from that moment, adaptation of the relevant code is very easy. And again, for the UI side, I think most of the testers is aware of this problem. For the especially for the front-end automation, it is very sometimes challenging tasks, because when I'm finding some elements on the page, then I can observe that at the next day I can observe that it is broken. My test is broken, right? Because why I'm observing the root cause of the breakage of the code, then I observe that maybe the selectors of the element is updated by the developers already, because I'm finding the element by its ID, and the next day the developer already updated the ID of the element. Then my test code is broken. And how can I deal with this problem? I can deal with this problem by, instead of using traditional selectors, maybe the ID, the expat of the element, all the traditional, I can just try to find the element by its visual representation. I mean, I can try to search the image on the page. And if I find the image by visual algorithms, visual detection algorithms, then even if its ID or its expat is updated, then my code will still work, right? Because it has nothing to do with the ID or the expat. It is just checking for the image or the visual representation of the element. So this is what we can do. And the code here I'm showing is a sample code from the test.ai. I think they have an open repository. And in most of the slides, I'm showing you some examples from different platforms, or some of them are commercial platforms, so you can check out how they work. So this is a sample code coming from test.api, test.ai library. And after developing test code, the next thing we do is to execute the test cases, to perform the executions. And how we can pull machine learning into play while or during our executions. What can we do with the help of machines? Okay, we can collect some statistics over the machines, right? For example, I have a sample test scenario, I execute it, and I collect some data from the execution. For example, the first thing that comes into my mind is I can collect the execution duration, right? I can collect this information, the statistics from the execution. And in the next time, I can again collect this data and see if something is unexpected, in an unexpected situation. For example, for most of the post requests, if I observe that an ordinary post request is executed in, let's say, 10 seconds, and if in one of the upcoming executions, if I observe that it is executed in not 10 seconds, but 30 seconds, then I can go and check what was wrong over that execution, right? So I can do that automatically, because I learned that a query should be executed in a known time range. And according to my learning, if I observe some unexpected situation, then I can go and check what the problem is. So during the execution, we can take advantage of the machine learning algorithms as well, because in all the stages, we can learn something. We can learn what the expected duration is, what the expected response is, a lot of learnings we can make. And according to the experiences, we can take some relevant action items in the upcoming, in the further test stages. And for the refactoring of the codes, we can again make use of the machine learning algorithms. For example, we told in the test code development part that we may have some anti-patterns in the code, right? For example, let's say what can be an anti-pattern in the code? Maybe if we have some numbers inside the embedded numbers in the code, then we call them magic numbers, right? So this is not an expected or this is not a best practice. So having a embedded number, having a magic number inside the code is not a best practice. So it is an anti-pattern. So if I teach machine that if a number exists there, which is not understandable to what that number stands for, then it is something to be solved, something to be refactored. If I teach this to the machine, then in the next reviews, if the machine observes some magic numbers in the code, then it can warn me, right? You taught me that having a number inside the code is an anti-pattern. It is a magic number. You told me this, and now when I provide some files to be reviewed, it can detect it and it can provide it back to me. Okay, you taught me, and now you have a magic number. Please correct it. So all the refactoring operations can be performed by the help of machine learning as well. And in these terms, we can reduce waste of time as well. And I guess we already discussed this. If our test code is broken somehow on the UI side, then it can be automatically fixed by the self-healing algorithms, because it can detect what changed and in the underlying update, if the ID of the element changed or if the expect changed, whatever is the changes, it can check the update that results in a break in the test code. Then if it can be somehow solved by changing a relevant with a relevant action item, it automatically corrects the problem. And in these terms, we can make use of self-healing algorithms to automatically correct, to remove the breaks in the test code. And finally, in the maintenance stage, sometimes we need some prioritization in our test cases, right? Because infinite testing is not possible. So we have some limited time for our testing activities. And we cannot test all the test cases, or we cannot have infinite number of test cases. So we need some prioritization in our test cases. And how we can do that? Again, we can make use of some experiences. We can make use of some learnings. For example, normally how I prioritize my test cases. For me, the test case which is most likely to find some bugs in the product is the most prior one. That is my prioritization criteria. Then how I can do it with the help of machines is, first, I can provide some data to the machine with the input-output relationship. For example, I provide a test case definition with a string value, and then I will provide the likelihood of the test case to find a bug in the system. For example, all the test cases which is written across one component in my system. For example, my system is a cloud-based IoT platform, and I have some services on my platform. For example, I have some asset management service or some connectivity services. If I know that from my past experiences, most of the test cases which is written to test IoT data upload test is finding a bug. If I know that, if I observe that, then this is an observation for me, right? I learned already that IoT data upload test cases are very likely to find some bugs. I learned this from the past experiences, and then it means that it is a very prior test case for me. I already make the prioritization, you see. So I can make the prioritization according to my past experiences, my past observations. So we can do this with the help of the algorithms. We can feed the algorithm with the relevant data, with the sufficient data, and it really learns how it works. Then it can make the prioritization instead of doing this manually. And the last stage in the testing lifecycle, we started with the definition of test cases. We continue with execution of and implementation and execution of test code, and finally maintenance of the test code, right? And now, after maintaining the test code, let's have an eye on the bug management part of test lifecycle. Related to bugs, what can we do with the help of machines or with the help of robots in our system? We can regard this from different perspectives. For example, we can monitor some clusters on the bugs. Okay, but what does it, or does it make sense to monitor some clusters? Because what is the meaning of monitoring some clusters on the bugs? We can see what kind of bugs are heaping together by seeing these clusters. I mean, maybe some bugs are heaped together on as just a certain feature, right? Maybe on a feature we have a plenty of bugs. By monitoring these clusters, we can observe if it is the case. If on a cluster all the bugs are heaped on just a specific product feature, if it is the case, then what can I do? Okay, this is a valuable information for me. Then I can go to the responsibles or owners of the specific feature, and I can ask, okay, I have lots of bugs on your feature. Do we have any problem on the configuration of the component? Or is it tested before going to the production? I can ask these questions to the owners of the relevant feature, and I can get some insights about the feature or components of the feature by monitoring some clusters. So the first thing I can do is to clustering algorithms on the bugs. And the second thing that I can do is some classification operations. For example, as I told in the beginning, I will show you very soon, a case study that is, again, a classification study. And we can classify the bugs according to their severity levels or their assignees or lots of different fields. So classifying these bugs according to their severity levels is very important, because sometimes I assign or I set a test case to severity 2, for example, very high severity level. Then if it is not really a high severity bug, then it can result in a waste of time. Because normally the first things that I want to solve is the most prior test cases, right? Therefore, or the other way around, if I set a test case to low severity level, but normally, in fact, it was a high severity, then it will be taken care by someone lately, right? We will lose some time because I did not make the prioritization or severity assignment correctly. So the triage of the bugs are very important. They are of very great significance. So doing this consistently is very important. And the bugs can really do that very consistently because it can observe all the previous samples. When I'm creating a bug, think yourself. When in your project, when you are creating some bugs, are you observing all the previous samples, or just regarding your own evaluation and then immediately assign to a severity level? That's what I'm mostly doing. I make my own estimation, I make my own evaluation, and predict that, okay, this is most probably something in severity 2. I am not checking all the previous samples, so maybe I am not acting consistently with all the other members in the team. Maybe I'm doing something inconsistently. And in these terms, machines can really make life easier for us because they are doing more properly and more consistently. And now let's see how it works on a real life project. In this project, I collect some data from our issue track system, which is Jira. And on this system, we have normally 6 different severity levels, starting from 1 to 6. And 4 of them are real bugs. I mean, 5 and 6 are not real bugs, but they are regarded as change requests, but not real bugs. So we have 4 different levels. And one of them do not actually exist in the system, because it is severity 1, and severity 1 is this severity level which is related to human life issues. I mean, if you have a hardware in the system and if there's a current leakage on the hardware, then it may result in a life loss, right? And it is a very dangerous situation. If we had such a case, we would have some severity 1 levels in the system, but currently we don't have in this real life project. So in short, I have 3 different severity levels, 2, 3, and 4. 3 different levels in the system. And I have almost 900 samples coming from the export of the Jira. And the first thing I do is to extract the features from these samples, because we are dealing with text, we are dealing with string values, right? For in some different scenarios, maybe we will be dealing with images, videos, something else. But now bugs are created with string values in the Jira, or we have some text values in the box, right? So the first thing I should do is to transform these strings into numeric vectors. That means feature extraction, and this is the representation of the extracted features from different samples. All different colors stand for different severity levels. For example, the red ones are the severity 2 samples, the green ones are severity 4, and blues are severity 3. So it is not that easy to interpret this representation, but still we can see some patterns between the features, right? For example, the first thing that we can observe is mostly we have some consequent samples. I mean, after a blue sample, it is very likely to have another blue sample. Maybe that's why we are performing documentation tests in a specific range of time. And during those time, we consequently create lots of documentation bugs. And in our project, documentation bugs are maybe 73, and most of the bugs created in that range of time are in 73. And after this feature extraction, by the way, let me talk about the methods to extract these features. Since we are dealing with some strings, we are mostly ensembling or embracing NLP techniques, natural language processing techniques. For example, we are dealing with TF-IDF approach to extract these features. And finally, after modeling over these features, now I will show you the results that we had. But firstly, let me show you the distribution of datasets. In this dataset, the distribution is as follows. Mostly I have class 2 samples, more than 400, almost close to 500, and less class 3 and 4 samples. And let's see the results. Let's see the confusion matrix over this distribution. It is like this, and the accuracy rate is 73%. Okay, it can be regarded as an acceptable success rate, but I think it is still maybe improved. It may be still improved. And after this observation, we started to think about the root cause for the weak success rate. What can be the root cause for the weak success rate? It can be an unbalanced distribution of the data, right? Because if you remember, I had mostly class 2 samples, and there is a bias on class 2. So as you can see on the confusion matrix, the most dark region is on the left part, on the upper part, on which I have 24 samples. So there is a bias on severity 2. The machine is tending to predict most of the samples as severity 2. So to get rid of this bias, what I do is, instead of dealing with class 2, 3, 4 samples, now I combine class 3 and 4 together. And now I will try to detect if a bug is class 2 or not. Class 2 or class 3 or 4. I'm regarding class 3 or 4 together. And why am I doing this? Does it make sense? Yes, because in my project, class 2 means a release blocker bug or a release blocker level. So if I have a class 2, then the according feature cannot be released. So having a class 2 or not really makes sense. So now I will try to see if I have a class 2 or not. Class 2 or other classes, other all classes. And now let's see the confusion matrix over this. And now I guess you can all observe. Now it's a much more balanced results. And the overall success rate is 82%. I think for most of the machine learning algorithms, it is still not in a perfect situation, because this study is really a very difficult one, because there is not absolute true in this study. I mean, there is not absolute facts in this study. I mean, if a test case or if a bug should be inserted 2 or it should be inserted 3, we cannot absolutely know this. It is a subjective evaluation. So maybe I am evaluating the results according to the actual results, which are filled by the human beings, which are filled by the members in the team. But what if they are not making a correct evaluation? So it is very likely. So maybe in the ones that I'm saying that the machine is wrong, maybe the machine is correct, right? We cannot know that. So it is since it is a relatively subjective issue, we cannot absolutely know the success rate. But eventually, I can definitely say that machine can learn all the past samples, all the past experiences, and it can really automatically assign the severity level of the bugs. So there can be still some feature works which can be adapted into the study, because I mean I told that I have 900 samples in the study, and it is a very small data set, right? Because for the machines we need a wide range of data. So instead of using this real life project, maybe we can adapt some different data sets from some other platforms. And in that way, we can improve the results maybe in the future. Or maybe we can construct or we can work on the entries to correct some typos or to improve the entries in the bugs. And I told that we can, apart from beyond classification studies, we can deal with some clusterings. And this is a sample result of the clustering algorithms. And we can see different clusters. And on some clusters, for example, on the first one, we can see that a sample group of bugs on which similar bugs heap together. And the first thing I can observe is there are lots of error words, right, on that cluster. I can observe that. I can see that immediately. So I can go and see if there is a problem on the response codes or the handling of the exceptions. The first thing I can check is that one, and I can get some insights. These clusters can provide some insights about the features or about different aspects of the features. And let me show you a visual representation of clusters. Again, it is not very easy and straightforward to interpret this visual representation, but at least we can see that they can be separated with some slices on the three-dimensional space. And we can really construct some groups to see similar bugs together. So that was the case study which is applied on our real life scenario. So we are closing to the end of the time that is reserved for this session. So let me quickly summarize what we discussed. We discussed that machine learning can be adapted in different software testing stages, right? Because sometimes software testing seems irrelevant to machine learning. Okay, I'm a software tester, and what is the relationship between machine learning and software testing? But we see that we can do lots of things in software testing stages, in different stages, with the help of machine learning, and it can really help us in different manners. And we can see different stages like test case definition, test case implementation, and maintenance of the test cases. We saw lots of different sample algorithms. And on this table, I show you some commercial tools and platforms which are doing that as well. You can go and check how they work. So as a result, we are able to get some help from machines, because normally there are different discussions whether they will replace me in my project. Can a robot can take my job from my hand? I think personally, apart from those discussions, we can collaborate all together. Instead of replacing the human beings in the project, the human beings can guide machines in the projects, and in this way we can do most of our work in a much more smaller time, and reducing the waste of time and reducing the waste of manual effort as well. So this is the end of my session. So we are very close to the end of the time. So, but still, I have some 5 more minutes. So if you have some questions, I will be more than glad to be answered them. But even afterwards, you have my contact information. So please do not hesitate to reach out to me. But firstly, let me check if we have any questions in the chat. Okay, for now we don't have. But I will stop presentation, but I will be here for a while more to answer your questions. Thanks so much for attending this, and enjoy the rest of the conference. I hope you are having a great time, and see you next time, and stay safe in these tough days. Thanks so much. Bye.